All right, so I think I'm recording. We're taking a look at skill packet 3, relations and functions, and I can't remember if it's 3E or what exactly subskill it is, but we look at how to build new functions using old functions. So they give us a function f and they give us a function g, and they say, hey, use this to build a new function. And maybe we build it maybe through addition or subtraction, and we looked at that already. And here, right now, today, we're focusing on building this new function through multiplication of the two functions. F times g will create a new function. F divided by g will create a new function, and g divided by f will create a new function. Well, given in a function, an important property and characteristic that we want to know about functions is its domain. So if we're asked to find the domain, if we're given the functions f and g, and we're asked to find the domain of a new function f times g, we can get away with finding the domain without ever finding the formula, the equation for f times g, which is kind of surprising, I think, because we can use the domain of f and the domain of g and intersect them, and that'll be the domain of f times g. Well, for f divided by g, we use that same intersection, but now we also have to include the fact that we've got a function in a denominator. And this function in the denominator, we have to make sure that there's no values of x that'll be in the domain that would cause that function to equal 0, because like I say, it's in a denominator and we can't have a 0 in the denominator. Well, then if we flip this, if we have g over f, the same thing happens. We're intersecting the domains of f and g in order for part of it, but we also have to be concerned that f could be 0, that the output, we don't want any input that causes the output of function f to equal 0, because f is now in a denominator. So these are the ideas that we have to try to apply to these problems, and we're going to look at problem number 2 and try to find the domain of each of these. Alright, so we start out with finding the domain of f and finding the domain of g. Given an equation, hopefully by now you've heard me say it once or twice, that the domain of any function is the set of all real numbers, excluding any values for which we have division by 0, excluding any values of x that cause us to take the square root of a negative number. Well, we don't have any square roots. We do have a variable in the denominator. So the domain of f is going to be all real numbers except the number 1. Because 1 minus 1 is 0, I can't have a 0 in the denominator. Alright, so then the domain of g, the same idea. I don't have any square roots, so I don't have to worry about taking the square root of a negative number. I have a variable in a denominator. That denominator can never equal 0. If x were allowed to be 2, 2 minus 2 gives us 0. So I'm going to prevent x from being 2. There's no way I'm going to allow you to input the number 2 into this function g. So if I want to find the domain of f times g, I intersect these two domains. And for some people, that's easiest to see by using graphs and saying, well, hey, if we have all real numbers except 1, this entire number line is shaded everywhere except at the number 1. And over here for the domain of g, I've got all real numbers shaded except for the number 2. Okay. And now, if I want the intersection of these two sets, I want the members that are in both. You have to be in this set and in this set to be in my final answer. So in my final answer, 1 is not shaded in the first set. It therefore is not in both sets, so it will not be in my answer. The number 2 is not shaded in my second set. It is therefore not in both sets, and it will not be shaded in my final answer. But everywhere to the left of 1, and we can go ahead and write 1 here, and everywhere to the left of 1 here is shaded in both of those sets. so it's going to be shaded in my answer. And everything that's between 1 and 2 is shaded in both, and everything to the right of 2 is shaded in both. So my domain for f times g is the set of all real numbers excluding the number positive 1 and also excluding the number positive 2. So there's my domain written in interval notation. All right, so that's for our first part if we want to call it part A. Now we want to find the domain of f divided by g. So we can use a huge portion of this work to help us do that. Let's erase the answer, a picture of our answer for the f times g, and we'll erase our f times g, and we'll come up here to where we intersected these two sets. That's what we did in this picture, and we now want to intersect the values of x that prevent the denominator g from being 0. So let's take a closer look at g. If g of x were allowed to equal 0, let's replace g with what it equals, 1 over x minus 2. If this fraction reduces to 0, it's because of the numerator. A denominator can never equal 0. So does this equation have a solution? Is this numerator of 1 ever going to equal 0? No. It's never going to equal 0. So hey, we're glad about that. There's no solution to this, meaning that we don't have to exclude anything. So there's no value of x that will cause g to equal 0. Okay, so that means that we have no added restriction to include in our answer. If we draw a picture of our final answer intersecting these three sets, then, because remember what these pictures represented, the first one represented the domain of f, the second one represented the domain of g, and the third picture represented the values of x that we threw out because they caused division by 0. All of these x's prevented g from being 0. So it added no new restriction. We've got 1 is not in the set because it's not in the original domain of, I guess not original, but the first function. And 2 is not in the domain of g. And so we get the same answer for f over g that we did for f times g. And sometimes that happens. And it's kind of nice when it happens that it's the same answer. So the domain of f over g is the same domain that we had for f times g, negative infinity to 1, or 1 to 2, or 2 to infinity. That's the same answer that, oh, I must have erased it, that we had for part A. All right. So in the last part, if I call it part C, I'm concerned about f being 0. So let's erase this. Let's erase this. We're going to save this other work, and we're going to change this g of x to prevent it from being 0 to say we're now preventing f of x from ever equaling 0. So what is f of x? Well, it's x plus 1 over x minus 1. Now, does this equation have a solution? Well, this time I think it does, because this fraction will reduce to 0 if the numerator is ever equal to 0, and that numerator will be 0 when x is equal to negative 1. I want to prevent that from happening. So I've got negative 1, which is to the left of positive 1 and positive 2. I can't let x equals negative 1 be in the domain for this function g over f. So I have to exclude it. Now, to be in my final answer, you have to be in the domain, you have to be in each set of these sets. You have to be in this one, and you have to be in this one, and you have to be in this one. So since negative 1 is not in all three of them, it will not be in the intersection. It will not be in my answer. positive 1 is not in all three sets, it will not be in my answer. Positive 2 is not in all three sets, it will not be in my answer. But it looks like everywhere else on the number line, none of these other values cause me division by 0 in any way. So there's a picture of my answer. I just now have to describe those. This is infinitely many numbers. I can't list them, but I can describe them using interval notation. So the domain for G over F is the set of all real numbers that excludes the number -1. It excludes the number +1. And it excludes the number +2. So there's my domain for G over F. And I hope that helps. I've got one more to do, and then that'll be it. So talk to you later.